Hello guys, welcome back once again. So now we will continue a problem. The problem is on differential amplifier. So it is NMOS differential pair with common mode apply voltage and so on and VDD 6 volts and all. So now let us draw the circuit. So this is NMOS differential amplifier with resistor RD. It's a basic differential amplifier. And the tail current which is given as 0.7 milliamperes, and they have given the resistor values which is 2.5k on the both sides, and this is connected to VDD which is 6 volts, and these two NMOS is energized with common voltage of VCM. And they also mentioned about the current source implementation. So they are saying this is implemented by a cascade current mirror. So we know the cascade current mirror, the headroom voltage that is nothing but the minimum voltage required to act as a current source. So was I'll call it as this as node P. So VP is the minimum voltage, so that the current source will be acting for its functionality. So that is overdrive voltage of these two MOSFETs, and the threshold voltage, that is VO1 plus VO2 plus VT, where VO1 corresponds to M1 and VO2 corresponds to M2. So in the question they have mentioned about overdrive voltage as 150 millivolts. So 150 millivolts plus 150, it would be 0.3, and threshold voltage as 0.5. So VP would be 0.8 volts. So this is the minimum voltage needed in order to act as a current source. So in the sub question A, it is asking about the aspect ratio of differential input transistor for the overdrive voltage of 150 volts, meaning they are asking the aspect ratio of this MOSFET. So I'll call it as W by L of 1. Now overdrive voltage, I will write down the expression for the overdrive voltage. VOV1 is equal to square root of 2 ID divided by mu n Cox W over L. So I'll write an expression. I'll separate out the WL and express in terms of VO and ID. So then it would be 2 ID divided by mu n Cox VO1 whole square. So 2 into ID. So ID is the current which is flowing in this MOSFET. So when this is 0.7 milliamperes, when the circuit is balanced, when the RD, all these resistor and as well as MOSFETs which are balanced, then the current would be ISS by 2, that is 0.7 milliampere by 2. So that would be 0.35. And mu n Cox, the value of mu n Cox which is given in the question is 60 micro. So I'll be substituting the same here. And the overdrive voltage of this MOSFET is 150 millivolts, which is given in the question. So 150 millivolts is 0.5 volts, 1.15 volts square. So after solving, I'll get the W by L ratio as 518. So this is which was asked in the question. Let us move to the sub question B. So it is asking about the magnitude of differential input voltage at which either of the input transistor becomes off. So when one of the transistor becomes off, say example here, when this becomes off, the current through this would be, I'll call it as ID2, will be equal to 0. So here the current which is ID1, which is entire current is flowing through this MOSFET itself when this is off. So ID1 would be then ISS, which is 0.7 milliamperes. So when one of the MOSFET gets switched off, the entire current will be steered towards one of the MOSFET. So let M2 get switched off, so that entire current will be steered towards the M1. So the current, which is 0.7 milliamperes, will be flowing through that. Then ID2 would be 0. So now I'll write down the since we are interested in what is the input voltage which is needed, so I'll apply a KVL on the input loop. So when I apply a KVL, so it would be I'll be starting in this from this point. So minus Vn plus VGS minus VT plus VP. So I'll write down the same, minus Vin plus VGS minus VT plus VP is equal to 0. So when I write down for Vin, it would be, I can call this VGS minus VT as overdrive voltage of MOSFET 1, which is VOV1 plus VP. Now VP, we already know it is the minimum headroom voltage of cascode amplifier, cascode current source. So that was around we got around 0.8 volts. The only unknown from this equation is the overdrive voltage. Now we shall obtain the overdrive voltage from drain current equation in the saturation, half mu n Cox W over L of 1 VOV1 square. So we need VOV1 from here. So then the ID into 2 divided by mu n Cox. We have all the data which is needed to compute. ID is the current which is flowing to the M1. Since I told like ID1 entire current will be flowing through this M1 itself, so ID1 value would be, ID value would be here 0.7 milliamperes, 0.7 milliamperes, and mu n Cox it's 60 micro. W by L is the value just we obtained, the aspect ratio just now we obtained in the sub question A. So after solving this, we get VOV1 as 0.21 volts. Then substituting the same in the equation here, Vin equal to VOV1 plus VP, which is VOV1 is 0.21 volts and VP is 0.8 volts. So we'll be getting as 1.1 volts. So this is the voltage which is required in order to make one of the MOSFET on and the other one off. M1 is on, M2 is off, and current, entire current is steered towards M1. So this is about the sub question P. So the next sub question is minimum and maximum values of common mode voltage, that is VCM. So this minimum, and let us find first VCM common mode max. So this common mode max is restricted, or this comes into picture because that MOSFET will be still in saturation and it will be working as it is expected, since the MOSFET is should be in saturation in order to work as an amplifier there. Because of that restrictions only, this common mode voltage max and all is defined. So we know the condition for the MOSFET in for saturation is VDS greater than or equal to VGS minus VT. So we can write VDS as VD minus VS, VDS as VD minus VS, and VGS as VG minus VS. We can strike this VS and VS, and VD and VD we shall write obtain an expression in terms of VDD and ID and all. So VD is the potential here, so VD would be VDD minus ID times RD. So this is the simple KVL which is applied here. VD is VDD minus IDRD. Okay, IDRD. So VDD is VDD minus ID RD. This is greater than, and at the gate voltage VG is common mode voltage is applied here, and so VG would be VCM. So VG is VCM, and VCM that is VCM max minus VT. So VCM max value is VDD minus IDRD plus VT. VDD is 6 volts. ID is the current which is flowing through one of the MOSFET, that is here. So when the circuit is balanced, so half of the current will be flowing through M1, the other half will be flowing through the M2. So half of that current, half of the 0.7 milliamps would be 0.35 milliamps. So half of the 0.7 milliamps into 2. RD value is 2.5K, and threshold voltage which is given is 0.5 volts. So 2 times 0.35, then 0.35 milli into 2.5. So we get VCM max as 5.625 volts. Similarly, we shall find VCM min too. This is defined or determined by the need to allow a sufficient voltage across VP such that sufficient voltage across the current source to operate properly. So only there is a limitation on the common mode minimum voltage. Otherwise the limitation can be anything, like it can go negative also. But if it goes negative, the current source which is sitting at the bottom won't work accordingly. So there is a minimum, the VC min is limitation is defined due to the current source. So once we apply the KVL on the inner loop in input side, so VCM is VCM min plus VGS plus VP equal to 0. This is just a KVL on the input loop. So VCM min would be, we can write VGS as VOV plus VT, VOV1 plus VT and VP. And we know overdrive voltage of M1 is 0.15, and threshold voltage also we know it is 0.5, and VP the minimum voltage headroom voltage for the cascode current mirror, that is 0.8 volts, and finally we'll be getting VC min as 1.45 volts. So this is the minimum voltage which can be applied at the gate of the differential amplifier, below which it won't guarantee as it will be working as a differential amplifier, because the current source won't work properly as it intended. That's it guys, thank you.